Okay, let's kick this off. It is Thursday afternoon on the last day of the conference, but rest assured, after you've eaten your lunch and you're sitting down in this room, we have a really interesting topic for you all that's going to perk you up and make your afternoon wonderful. A couple of things before I introduce the speakers here today and their topic. Please hold your questions to the end. We will try and make time for them, and I'll run around with the mic if we have time at the end. But please welcome to the stage. I'm going to read this because it's a long and complex title, and I want to get it right for everybody. Presenting running high-performance user space packet processing apps in Kubernetes, we have Abdul Halim from Intel and Peng Liu from Red Hat. Please welcome them to the stage.
Good afternoon, thank you. Thanks for joining this session. So this session is about how to run high-performance user space packet processing apps in Kubernetes and what capabilities is needed and how you do it. So this is just regular legal and disclaimer, so you can read it in your own time. So the topics that we're going to cover is that we'll first talk about why do we care to running such application in Kubernetes, and the challenges and overheads that involve, and how do you utilize the NIC's full running rate. And we'll briefly introduce the DPDK if you are not familiar with, and then we'll talk about the sample deployment that we use for the demo. Then we'll talk about all the capabilities that needed in Kubernetes to run the DPDK application. And SR-IOV networking is a big part of this demo, so we'll talk about that as well, how the SR-IOV networking is done in Kubernetes. Then we'll talk about the SR-IOV networking operator, that is how that simplifies the whole process. Then that will be followed by a recorded demo that we have recorded in our lab. So this is just briefly something about us. So my name is Abdul Halim. I'm working in Intel as a cloud software engineer. And
hi, everyone. I'm Peng Liu from the CTO office of Red Hat. I'm living in Beijing, and I'm focusing on enabled NFA use cases with open source software. Thank you.
Thanks. So let's talk about the motivation. So someone may ask, why do you want to do such things in Kubernetes? Why do you want to run a packet processing application in Kubernetes? So I think the 5G is a great example of this kind of use cases. We all super excited about 5G. And there were some great talks and demos related to 5G already seen. There's a nice demo shown by Azhar Saeed yesterday, live 5G demo in the keynote. So we thought that it would be great to see that what is required to run the 5G network infrastructure application in Kubernetes and how we do it. So there are some, these are some of the fundamental promises that we expect that 5G will deliver by 2020. So this it was supposed to see a greater throughput, that is like 50 plus Mbps for each network device, and lower latency, ultra high reliability, and for service such as e-health. And then we have much higher connectivity density and more user mobility as well. So all of these translate into the more network need to be more faster and faster. So as all you know, that network hardware are already capable of delivering this higher throughput, but the problem always goes into the software stack. That software stack sometimes it cannot keep up processing that throughput. So for 5G also depends on Kubernetes. That's because for the speed and the scaling that it offers, and we already seen that 5G is deploying on Kubernetes. So what we want to see is that what it is required to run this kind of application, and we can utilize the full NIC capabilities in running this kind of application. So this two table shows the challenges that we see. So with the table at the left-hand side in the blue shows the NIC capabilities, and right-hand side on the green, it shows that how much is time constraint it put into the software stack to process this kind of throughput. So as you can see, the smaller the packet size is, the smaller the time we get into process each packet. So the higher the packet rate, the lower the time it to process, and to achieve the zero packet loss, network stack must be less than the packet arrival rate. So this overhead in kernel, so as we can see that for the smallest packet frame, which is 85 bytes in Linux, and there is 67 nanosecond to process, and which is translated like about 201 CPU cycles in 3 gigahertz CPU, which is very small time in comparison if you want to do a smaller packet, and there's like for 10 gig NIC, this is really challenging for software stack to keep up with. Here you can see what overheads in kernel introduce. So a lot of these cycles could be spent on context switching, system calls, interrupt handling, lock and unlock to copy the buffer from a kernel stack to the user space. And also there's a chances if there's a cache misses, then your penalty also much higher. So how do we utilize the full range rate? So there's the two options. First of all is by try to improve the kernel stack, and other is the bypassing the kernel. So there's the bypassing the kernel there's a different way of doing it. One is the DPDK, which is the data plane development kit, which is a library and driver, user space driver that offer to do this kind of packet processing in the user space instead of the kernel stack. And there's also RDMA and XDP as well. So in this session, we focus on the DPDK because DPDK is the well-adopted library for implementing the BNF application. So this is about the DPDK. DPDK is an open source project that offers a framework to do the packet processing application also, as well as the poll mode driver that runs in the user space as well. So I'll not go much detail into DPDK. There's a lot of documentation already covered that. So our focus is not there. But what we want to see is how DPDK does that. So DPDK basically is it takes the dedicated processor instead of leaving into the Linux scheduler to randomly schedule in the different processor. It takes the dedicated CPUs, assign it to the certain device, and the driver runs in a poll mode. So basically, the driver constantly pulling the packet from the interface and giving it to the application directly. And it also offers the lockless synchronization, so you actually don't need to do lock and unlock, and also it utilizes the ring buffer as well. And the packets also process in the batch instead of processing each single packet, so that also adds some additional improvement. But DPDK also comes with caveats, so it's for guaranteed performance. It requires optimal resource allocation and tuning. So it requires exclusive CPU to be given for this application, and also you need to give a direct I/O devices for NIC, for example. And DPDK also need a huge page memory, so to reduce the TLB cache misses. And all of this also require NUMA alignment. So these are the key requirements in Kubernetes that needed to run DPDK application. And the challenge here is to resource allocation and management, all of these. So the device and the CPUs and the NUMA alignment as well. So this session is about all these capabilities that need in Kubernetes to orchestrate the resource critical DPDK apps and how to do it. So on this demo, that what we show in here is we basically use two DPDK applications deployed in the Kubernetes. For one of them is the generating the packets, the DPDK packet gen, other is the DPDK test PMD. So what we are doing is using two interface. One of them is the Kubernetes control plane, the ETH0, and other net0. You can see that is the data plane interface. That's basically getting an interface, a virtual function from the SR-IOV NIC. And test PMD also similar setup. It's getting another BF from the other port, and basically packet generator generates packet, and test PMD receive that packet and basically just do a loopback and transmit back to the same port and receive by the packet generator. So we want to see that we can achieve the full run rate from these applications. So this is the platform that we utilize in the lab. So this is the old per server with a 2-socket system, and we use the Intel Xeon Cascade Lake, the latest the processor there. And also we use the XSB710 Intel 4-bill NIC for this. This is 2 by 225 gig port. So this is the example of the test PMD that the parameter is accept. As you can see that it requires the exclusive CPUs, and it also need the I/O device, the NIC PCI address, and also it requires the NUMA alignment as well. So you got maximum performance to do this kind of high throughput packet processing. So all of this, as you can see, these are the resources that you need to be given when you deploy this pod into the Kubernetes. So any orchestration platform need to ensure that these resources are properly managed and accounted for maximum resource utilization. So the required capabilities that needed in Kubernetes is the exclusive CPU. So Kubernetes should be able to give the workload the exclusive CPU access, and also huge page memories and direct device assignment for SR-IOV kind of devices, so that pod can get exclusive access to those devices as well. And also all of these resources need to be aligned with NUMA. So you don't end up with in multi-socket system that CPU and memory in one NUMA socket and your device in a different NUMA zone. So there is no crossover. So other components that we needed is basically this is the SR-IOV network that we implemented. So we need to have a SR-IOV networking capability as well. So for that, we have SR-IOV network device plugin that does the resource allocation and resource discovery and registration to the Kubernetes, the kubelet, and then SR-IOV network, SR-IOV CNI that does the port configuration. For example, if you want to configure a VLAN or the rate limit or things like that, you can do that through SR-IOV CNI. And we also have the SR-IOV network operator. So there's a lot of configuration need to be done for the both SR-IOV device plugin and SR-IOV CNI. So SR-IOV network operator simplify those processes. And also for the pod spec, you need to give the certain resource request and the network attachment definition as well. That's been taken care of by the pod the AppNet util, which is basically get those parameters from which devices are given for those workload. It gets those parameters, and what we see in the test PMD, it added those parameters, so you don't need to go in the pod and figure out what device and what CPUs are being allocated. So that's AppNet util, the framework provide those information. And there is also the network resource injector that basically adds those the required resource allocation for the pod spec as well. So we'll see them into detail later on. So this is the software configuration used for this demo. So this is just for the reference. So here we'll see that how to get the exclusive CPU for the workload. So to workload to get the exclusive CPU, it needs to be run in the guaranteed QoS. So for guaranteed QoS, and you're familiar with Kubernetes CPU Manager, you need to request both CPU and memory request, as well as the CPU request must be integer values. So this is so in this example, you can see that we put the CPU values for 2, so which means that we're looking for 2 exclusive CPU for the workload. And for NUMA alignment, which is we have to work on also for topology manager that is part of now V1.16 as alpha feature. So topology manager, what it does is basically ensure that your CPUs, memories, and devices are all aligned with the same NUMA socket. So to enable the topology manager, so this is the feature get that you need to enable using the topology manager equal true. And also, you need to specify what policy the topology manager will run. So there's 4 policies: the none, best effort, restricted, and single NUMA. Best effort doesn't guarantee that you will get the NUMA alignment, but the restricted and single NUMA will guarantee that you will get the NUMA alignment of all of these resources. So in this example, we use the single NUMA node policies. To request a huge page, so you need to request as an empty volume. So the huge page will be, first of all, you need to create the huge page on the platform, and then kubelet will register this with the Kubernetes API, and in the pod request, you need to request as an empty volume, and you need to specify the limits and request as well, that how much you want. But one caveat with the kubelet is that you can only have one type of huge page. Even though you can create two 2 megabyte huge page or 1 gigabyte huge page, but kubelet only advertise one type. So that need to keep in mind. So this is how the SR-IOV network device plugin is implemented. This is the graph probably look a little bit complicated, but as you can see, the orange part is the main 3 components that are needed to enable SR-IOV networking. So as we can see, in the pod, we have the SR-IOV BF added as an additional interface. It doesn't replace the default H0 network that for the Kubernetes control plane. So for that, we need a Matter plugin that can enable to add multiple interface, more than one interface in a pod. So we use multis. And basically, SR-IOV device plugin does the device discovery and register to the kubelet, and the kubelet then transmit back to the Kubernetes API. And when pod requests through the extended resource, it gets allocated when the pod is created, and the multis retrieves which BF was allocated, and then it passes on to the SR-IOV CNI looking at the network CRD, and the SR-IOV CNI does the port configuration for that BF for this pod. And so this is the steps I already explained. So SR-IOV device plugin works on a config file. So that config file defines that how many resource endpoint you would like to create. So you can actually separate out your SR-IOV BF with a multiple resource endpoint. So basically saying that this is the type of device I want into this resource endpoint name, so you can identify them easily. So in this example, we are basically targeting BF from the 2 different physical functions, which is first port, and the other one is from second port. So after the device is discovered, the device plugin will register them with the kubelet, then register them as part of the node information, which will be reflected in the Kubernetes API server. So this information can be used during the pod scheduling. So this is, so the overall steps is like that. So you'll, once the device plugin registers the devices to the kubelet, then we need to create a network attachment CRD, which is just basically saying that how we would like to configure those BF. And then in the pod spec, we need to refer to this network attachment CRDs. By the way, this CRD is used by the multis. So multis is a network plumbing working group standard defined for this network CRD. And also we need to specify the resource request for that, how many BF we need for this network. So as you can see, there's a lot of steps to just to configure the SR-IOV networking. So we need something that can simplify this whole process. So with that, we have developed the SR-IOV network operator. I think Peng Liu will explain you on that the capabilities.
So let me give you an introduction on the SR-IOV network operator. So the SR-IOV network operator is a tool to hide the complexity of configuring the SR-IOV components in Kubernetes. So it provides some automation to the, for example, the lifecycle management of the SR-IOV software component, like the SR-IOV CNI plugin, the SR-IOV network device plugin, and the network resource injector, and so on. It also manages the configuration of the SR-IOV software components. For example, it will generate the configuration file for the SR-IOV device plugin. And also, it configures the hardware in your worker node. So which means SR-IOV is a hardware related feature, so you need to set up the hardware to enable that. So the SR-IOV network device, the network operator will help you to configure your hardware, SR-IOV hardware on the node. It also discover all the SR-IOV capable interfaces in your worker nodes. And in the end, it can also load different type of kernel driver to your node. For example, if you are using the DPDK application in your pod, you need to load the VFO driver instead of the default kernel driver. And at the last, it also generated the network attachment definition for the SR-IOV network you created. So the SR-IOV network operator is built for OpenShift. However, it can also work with vanilla Kubernetes. So if you are interested, you can just try it in your cluster. Well, in this slide, you can see the workflow of how to configure the SR-IOV function in your cluster and how to you consume the SR-IOV feature. So for user, you should only care about the steps in red. So first, we launch the SR-IOV network operator. Then the SR-IOV operator will provision the SR-IOV network config daemon on each worker node. So the config daemon will discover all the SR-IOV capable hardware in your cluster and report it back. Then the cluster admin can choose on which node they would like to enable the SR-IOV capability, and they would like to configure the virtual function for this hardware. So they can create a SR-IOV network policy. For that, so then the operator will configure the SR-IOV device accordingly, and it also will generate the configuration for the SR-IOV device plugin. So if you need to load the kernel driver, it will also do that for you. However, it doesn't take care of the BIOS side. So if you need to enable the, for example, the VFO driver for your virtual function, you have to enable the IOMMU in your Linux boot parameter, which cannot be done by the network operator. So the third step is to create a SR-IOV network with all the virtual function you just created on your worker node. And in the end, you can just create a user. So for the first three steps, it can only be done by the cluster admin. And at the end, the user can create their pod manifests with all the information needed. So next is a manifest example of SR-IOV network customer resource. So here you can see that there's a one-to-one relationship to the network attachment definition, which will be consumed by Maltus. So you can see that we can specify the namespace where you would like to create the network attachment definition, and you can specify what kind of IPAM you would like to use for this SR-IOV network. And you should also give a resource name, which will be aligned, should be aligned with the resource name we used in the network SR-IOV network device plugin, and also aligned with the resource name we can see in the node information. Well, the second customer resource definition is the SR-IOV network node policy, which basically is you specify which node you would like to configure your SR-IOV devices. And in this node, there might be several SR-IOV capable devices. So for which devices you would like to select to configure the virtual function, and you can configure the MTU for the virtual function. So all those information will be consumed by either the SR-IOV network config daemon, so that it can configure the hardware for you, or can be consumed by the operator to generate the config file for the SR-IOV network device plugin. So next, this one is the SR-IOV network node state custom resource, which should be only maintained and updated by the operator itself. So as a classic admin, you should not do any modification to it. It will be maintained by the operator itself. However, you can get the information from it. So let's check out the status first. The status will be updated by the SR-IOV network config daemon, which running on all the worker nodes. So it contains all the hardware information you may want to know. So what kind of devices you got on the host, and you can find the MTU, the current MTU, the number of virtual function which can be configured for these devices. And after you created the virtual function, you can also find the information about the virtual function of this interface. So in the spec set, in the spec field of this customer resource, it is the desired state of the node, which you be generated according to the network node network node policy, we just mentioned in previous slide. So let's do the demo. We have a record demo for this. So here is my cluster. In this node namespace, there's no pod yet. And here's my cluster. I have only one bare metal worker node here, and with 36 1 gig huge page configured. Then let's check the kubelet configuration. So the topology manager is still an alpha feature in 1.16, so we have to turn it on. And we also need to specify the policy of topology manager and the CPU manager. Here we use static for the CPU manager and restricted for the topology manager. Now let's start the operator. So after this operator is started, it will provision the config daemon and the network resource injector. So here you can see that we can find all the SR-IOV capable devices in this node. So in this demo, we will use these two devices. Now we apply the policy and create the network, the SR-IOV network customer resource. So after creating the SR-IOV network node policy, it will generate the configuration file for the SR-IOV device plugin accordingly. So here you can see that we have two resource pools. One is NIC1, the other one is NIC2. And the network attachment definition has also been generated accordingly. So there's two network created. After that, we can say that the SRV CNI plugin and the SRV network device plugin has already provisioned to the worker node. So now we can see that the hardware resource has been reported to the Kubernetes API server. So now we check out the manifest of the pod. So the first pod is the test PMD pod. We assign the NIC1, the virtual function bound to NIC1, and for the package generator pod, we put it in the attach it to the virtual function in NAT2. Now the pod is up and running. Let's get into the pod. So in the right side of the screen, we go into the part of test PMD. So here you can see that we can retrieve the information of, for example, the CPU which bound to this pod and the PCI address of the virtual function. Now let's check that they are NUMA aligned. You can see that all the CPU we use for this pod is in NUMA node 1. Then let's check if the NIC is also, yeah, you can see that the NIC is also in the NUMA node 1. So we are in the same NUMA node. Then let's start the test PMD application. So in the left side, we go to the part of packet generator. So let's start the packet generator. Then we get the MAC address of the test PMD pod. So we use that for the destination MAC address of the traffic we would like to send. Next, I set the packet size to 512 and clear the statistic of test PMD. Now let's start the traffic. So here you can see that in the packet generator, the packet has been sent and received from the SRV virtual function. And let's also check the statistic of test PMD. So here you can see that there's no packet drop or loss in RX or TX direction. So basically, that is what we demoed today. And let's switch back to the presentation. Also, here you can find the video record in YouTube, and also all the manifests we use for this demo. You can check it out if you are interested. Well, still there's something we need to pay more attention. For example, the isolated CPU support. Currently, if you specify CPU, isolate CPU in the boot parameter of Linux, it cannot manage by Kubernetes, cannot manage by Kubernetes, which could be a problem since for a telco use case, we would like to use those CPU dedicatedly for packet forwarding. And also, there's some out-of-tree solution for this problem. However, we would like to see a more upstream solution for that. Since none of them are well integrated with native CPU manager, we already have in Second, there's no topology-aware scheduling for these things. So at this moment, we have CPU manager and the topology manager in the Kubernetes set, but for the QB scheduler, it cannot, they don't know the information of NUMA topology when it do the scheduling. So in the worst case, it may result in the path schedule to a non-valid node.
So yes, so a lot has been done in the community to support this telco and the 5G use cases in Kubernetes, and we can say that Kubernetes is 5G ready. We have seen the demo yesterday as well, and it has been deployed in Kubernetes. But there are some areas that still need some attention, and we need a wider community collaboration and involvement. So with that, I think the presentation is finished. These are the references that you can check, and there are some additional resources that you can see. That's all this component we discussed today. You can get some application note and feature brief as well on those. So thank you very much, and if you have any question, I don't know if you have time.
Wonderful. Thank you very much, Abdul and Peng. They'll be around to take some questions, but please move towards the back of the room so we can clear it for the next session. Thank you very much.
Thank you. Thanks.
Thank you.
We can talk in the back.